Hi, welcome to our first class for Introductory Physics. This is an algebra-based class on physics, and the primary difference in my mind between this class and a calculus-based class is that we focus more on the concepts, whereas a calculus-based class we tend to focus more on problem solving and applying calculus to problem solving. It's just a different weighting. So my hope is that from this class you will gain an understanding of basic concepts of physics. For many students, this class is a required class for their major and may not have been their first choice for a class to take. I think that was true for my own daughter when she took physics, so I acknowledge that, but I hope by taking this class you will recognize why it's a requirement, and that is that physics is a fundamental science to the other sciences, to biology, chemistry, and so on. From the components of an atom to the components of the cosmos, those all fall under the umbrella of physics. For those of you that are environmental science majors where this is a requirement, there is a lot of physics that is part of environmental science and geology. So I hope you'll find those applications helpful. Indeed, that is my background, is geophysics. So if that is an area of interest to you, feel free to reach out to me during office hours and so on. We can explore that more. For those of you who are pre-meds, I hope the concepts of this course are helpful throughout your career, from understanding the mechanics of the torque on a joint to understanding the physics behind imaging systems that are used for medical testing. So as we start the class, we'll go over that was a bit of an introduction to physics, and we'll go into measurement and estimating, and also some basic concepts for science. So nature of science, physics and its relation to other fields, which I basically just touched on very lightly, models, theories, and laws, understanding these definitions and how they are similar and different from each other, then some nuts and bolts to get us started. Measurement, uncertainty, significant figures. This may be review, but we do need to go over it. Units, standards, and the SI system. Again, that may be review for many of you, but it's a key part. We will use this knowledge throughout the entire course, so it's important that we spend time going over it. Understanding how to convert units is also a critical skill. Hopefully you'll get, even if you already know how to do the mechanics of it, I hope that by the end of this lecture you might have a better insight as to why the steps you take to convert units works rather than doing it by rote. Order of magnitude rapid estimating can be helpful, as can dimensions and dimensional analysis. So let's begin with some terminology and insight into sort of the nature of science. So I do scientific research. I've been funded from the National Science Foundation, from the Air Force, from NASA. In all of these cases, the research follows a similar cycle, where one takes some observations. Observations are an important first step towards scientific theory. And when you have a set of observations, it's important to have some imagination to tell what is important. I remember my doctoral advisor once said to me, there are many ways to study the communication system of this country, but studying the telephone poles, or today the cell phone tower placement, might not be the most helpful approach. So realizing what's important depending on the question that you're asking. So you have some observations, you may create a theory then to explain your observations, and from the theory you can make predictions, and then this is where you might write a proposal to say, this is my theory, if this is right, then this is what I predict, and if this is the case, then we expect to see this. And then you can potentially run an experiment, make additional observations until the prediction is accurate, and then the cycle repeats itself. So that's a fairly standard path in science. In fact, often somewhere along this path, something doesn't go as planned, and then we make new discoveries. But barring those, special moments in science, this is a fairly normal cycle. So I use the word theory here, and I do want to make it clear that the term theory has a different meaning in science than it does in the common vernacular. So from Wikipedia, I pulled up this definition in everyday speech. Theory can imply an explanation that represents an unsubstantiated and speculative guess. So you might think of conspiracy theory. You might think of someone saying, I theorize such and such, and it sounds right, unsubstantiated and speculative. That is not what it means in the scientific discipline. Within science, a theory describes an explanation that has been tested and is widely accepted as valid. The dual use of the word theory between the vernacular and the scientific causes a lot of, I think, unnecessary confusion when it comes to trusting science. Because if people hear that there is a theory of climate change and they don't understand that within science that describes something that has been tested and widely accepted as valid, whereas they hear the word theory and may think it is something unsubstantiated and speculative. So it's an important differentiation for usage. And I think it's rather unfortunate that the word theory is what is widely used in science and has this dual meaning. Okay, so moving on, let's give a few more definitions. We'll go through the differences between model, theory, and law. So model to me is quite a separate category from theory and law. So model is an analogy or a mental image of a phenomenon in terms of something else with which we are familiar. So an example might be the wave model of light. So we talk about light as waves, and we might relate that, and I will relate that when we cover that topic, to wave motions in water, because we can visualize waves in water, whereas we cannot visualize waves of light directly. We cannot see a light wave, but we can see a water wave. So a model is a nice analogy or mental image. They give us this mental or visual picture, and this can hopefully give rise to a deeper understanding and lead to new ideas for new experiments and about what related phenomena might occur. If you notice how waves reflect off of a barrier, you might wonder if light reflects in a similar manner and conduct experiments, for instance. So that's a model. It's an analogy. It's not the real world, and it doesn't try to be the real world. There are always simplifications. So again, it takes that creativity. What's important? What are we trying to understand? A theory tends to be broader than a model. It's more detailed, and it provides quantitatively testable predictions. So this gave us some more qualitatively testable predictions, although computer models can give us quantitatively testable as well. But a theory tends to be more broad, quantitatively testable predictions, but it's still not the real world. And then a law, still not the real world, it tends to be a concise general statement about how nature works. And the law might be, an example of law might be energy conservation, that energy cannot be created or destroyed. It is always conserved. Another law might be conservation of electric charge. Another law is Newton's second law of motion, F equals ma. And I would note that while this is a concise general statement, a law isn't necessarily true under all conditions. And indeed, if you take the second half of this course, when we get to Einsteinian relativity, we'll see that Newton's second law of motion isn't this simple. It isn't just F equals ma if you start having velocities near the speed of light. All right, so let's say you are working along in science and you have a new theory. How does it get accepted? In general, it's when your predictions from your new theory agree better with the data than an old theory. Your new theory explains a greater range of phenomena, of observations. So an example is Ptolemy had a geocentric model for the solar system, where here's the Earth at the center of the solar system, and then this nice fiery ring is the sun, which orbits the Earth, and then the moon, and then the other planets moving outward. And that was replaced by Copernicus, who had heliocentric. We have the sun at the center of the solar system, orbited by Mercury, Venus, the Earth, the moon orbiting the Earth, and so on outward for the planets that had been discovered at that time. And you can see that both of these have circular orbits. We'll get even closer to an accurate predictive model if we make these orbits elliptical, and so on. So we continue to have improvements in our models. All right, so I think I already said physics is the most basic of the sciences. It's needed in architecture and engineering, for instance. I think that's fairly obvious. For instance, here's a nice image from Da Vinci of the stresses in building an arch and the keystone, and mitigating having an arch collapse. So that was a study on forces by Da Vinci. Other fields, as I mentioned, also use physics and make contributions to it. Physiology, zoology, life sciences, earth sciences, chemistry, and so on. So often today we will have teams of people working on a project. So communication between, say, architects and engineers, or between the physics technician in a medical lab and the individual who's interpreting the results to understand, why things are working the way they are, if there are problems with the system, and so on. Communication between different groups is critical. And here's a nice example of how important it is, say, to have communication between architects and engineers. Here is a Roman aqueduct, which still stands about 2,000 years after it was first built. And here is a collapse following an earthquake. I believe this was following the Loma Prieta earthquake in California. All right, so we've already talked a bit about models, theories, and laws. One other term that might come up is a principle. It's similar to a law, but has a narrower range of phenomena. An example that we cover in the 2 course sequence is Archimedes' principle. That term will show up then. All right, so moving on, there's a lot of emphasis on uncertainty as part of the lab portion of this course, so I will not stress it as much in the lecture portion because you'll have plenty of practice with uncertainty. But I do want to make sure we understand the concept of it. So no measurement is exact. There's always some uncertainty due to limited instrument accuracy and difficulty in reading the results. So the photograph to the left is an example of this. So here is a 2x4 being measured by a ruler here. And if you were using the centimeter scale here, you can see that with this board and this ruler, it would be hard to estimate to better than a millimeter. So there's going to be, if you had 8.5, 6, 7, between 7 and 8, it looks like here, somewhere in there is probably the right width. So if you measured that as 8.8, our uncertainty would be 8.8 plus or minus 1 millimeter or 1/10 of a centimeter. 1/10 of a centimeter is a millimeter. So that would be a way of writing our uncertainty. Sometimes we want to have a percent uncertainty, and that is the ratio of the amount of uncertainty to the measured value. So the amount of uncertainty in this case is 0.1 centimeters. The measured value is 8.8. So 0.1 divided by 8.8. And then to get that into a percentage, we multiply by 100. And this gives us there's about a 1% uncertainty in that measurement. The next thing I want to talk about is significant figures. We do need to be able to keep track of significant figures in this chapter. After this chapter, I am not going to care about significant figures. I want to be able to focus on the physics, and I'm happy if you report your homework to 3 significant figures. Within the lab, they will probably continue to want you to keep track of uncertainty and significant figures throughout the term. But for the homework for the class, I won't care after this chapter. For this chapter, I do care. I want to make sure you know, if you need to, you can keep track of significant figures. So let's look at some examples. We can usually tell the number of significant figures by the way the number is written. This 23.21 has 4 significant figures. If we're given all of these values, they are all significant. Leading zeros don't count, so 0.062 leading zeros don't count. Imagine if it were 00100. If it weren't past the decimal point, it might be more obvious to you. If this had been 0023.21, that wouldn't add any more significance to our measurement. Those leading zeros wouldn't count. Same is true if it's to the right of the decimal point. So there are only 2 significant figures here. When we have trailing zeros, it can be more ambiguous. So if we have an 80 without a decimal point, we're assured that we have 1 significant figure, so it could be to the nearest tens. It's possible that the 0 is also significant. To designate that, we'd really want a decimal point here. If there were a decimal point there, I could be confident that that was significant, but as it's written here, it's a bit ambiguous, and we could be only sure that we're accurate to 1 significant figure. If we were measuring 80 kilometers accurate to, say, 3 significant figures, it should be written like this, if we're going to do it as 80. We can also go to scientific notation, which we'll get to, and that's preferred because we don't get these sorts of ambiguities. All right, so for this class, we can assume that a number such as 6.4 is accurate. So this is different from number of significant figures. So a number such as 6.4 has two significant figures, and we will assume it's accurate to the 10th place. If we're given 950 without a decimal point, we'll assume it's accurate to the tens place, plus or minus 10, unless 950 is said to be precisely or very nearly 950, in which case we'll assume it's to plus or minus 1. So the wording matters. I will try not to be that ambiguous. I'm creating the homeworks, so I don't have to have this sort of ambiguity that has existed in some questions in past years that have come out of textbooks. All right, so let's move on to applying some of this knowledge. When adding or subtracting, if we have to keep track of accuracy, a number or a result is only as accurate as the number in your calculation with the least accuracy. So if these were all, say, centimeter measurements, and we were adding them together, this was accurate to the thousandths place, this was accurate to the fifth decimal place, this is accurate to the hundredths place. So our least accurate is this value, accurate to the hundredths place. So after we do all the addition, and we can talk about rounding, but after we do all this addition, our result should only be accurate to the least accurate measurement. So only 2 places past the decimal. Notice we didn't have to worry about significant figures here. We worried about the accuracy of the value. So in addition and subtraction, pay attention to the accuracy of the value. Let's give another example. This 3.6 minus 0.57. If you did that on a calculator, you'd get 3.03. But again, this is an addition or subtraction. So our solution should only be as accurate as our least accurate value. And this one was accurate to the tenths, hundredths here. So the tenths this is our least accurate value. So our solution should just be to the 10th. When multiplying or dividing, our solution should only be as accurate as the number with the least number of significant figures. So if we multiply 2.0 times 3.00 times 4.000, this is 2 significant figures, 3 significant figures, and 4 significant figures. We multiply that through, we get to 24. This value to the left only has 2 significant figures, so our answer should only have 2 significant figures. All right, let's try another example. What if you want to multiply 11.4 centimeters by 6.9 centimeters? This is 3 significant figures times 2. Our solution, if we do it on a calculator, would give us 78.66, but the answer should only be accurate to 2 significant figures, so I've rounded the 78.66 to 79. The other thing I would note here, we'll talk about this more, but when we multiply values, units also have the same, get multiplied and divided as well when we're doing arithmetic multiplication or division. So if we multiply centimeters by centimeters, we'll get centimeters squared. And you may think of this in terms of, say, a length times a width gives us an area. All right, another example, if you divide 2 by 3 with 2 significant figures and 3 significant figures, on the calculator that would give us 0.666 repeating, but our answer should only have 2 significant figures if we're keeping track, so I've rounded that to 0.67. I think the only place people would have question with rounding is if this had been, say, 0.555 repeating, I would round that to 0.56. And we'll have other examples of that as we go through the class. All right, so calculators, you may have gotten a sense of, don't always give you the right number of significant figures. Often they give you too many. So this 2 divided by 3 gives us 0.6 repeating, and our solution should, as written here, should only have 2 significant figures, so 0.67. At the bottom, if we multiply 2.5 times 3.2, that equals 8, and we got a solution with just 1 significant figure. But given these inputs, the solution should have 2. So if you're writing that and you're keeping track of significant figures, it should be 8.0. To help keep track of significant figures and to know whether, say, trailing zeros are significant and to not get confused about leading zeros, scientific notation is one of the ways that's very helpful. So we often write numbers in powers of 10 or scientific notation, and my preference for this class is to have a leading digit, decimal point, and then the trailing digits. In engineering, there are often 2 leading digits. In other sciences, you might have no leading digit. You might go 0 point and so on. So there are different standards. I like the 1 digit, a decimal point, and then trailing digits. That's commonly used. So if you wanted to write 36,900, you could write that as If there are only 3 significant figures, you'd write it as 3.69 times 10 to the 4th. If either of these zeros were significant, you could add trailing zeros here, and that would become clear that they're more significant figures. 0.0021 you can write as 2.1 times 10 to the minus 3, and so on. So how can you figure out how to go back and forth between these numbers? For the value on the left, imagine where the decimal point is here, and if you want to get that to 3.69, you have to move the decimal point 1, 2, 3, 4 to get to 3.69. So 3.69 times 10 to the 4, that'll give you the right number for the exponent. 10 to the 4 is 10,000, so you could do a quick check. 3.69 times 10,000 will give you 36,900. So you could just check back and forth. Similarly, if you have to move the decimal point to the right to get a leading digit and so on, we have to go 1, 2, 3 digits to the right. When we go to the right, it's a negative exponent, but it's 3. So we have 2.1 times 10 to the minus 3. So you might play around with that. There are a few other examples here as well. The difference between 300 without a decimal point, so it's only one significant figure, and 300 with a decimal point, so there are 3 significant figures, are shown here. All right, so let's move on to standard measurements. Traditionally, our standard quantities were defined in terms of some object, say a meter stick, or the kilogram was a platinum-based ingot that was in Paris. But now all of the basic quantities are measured in terms of fundamental constants. So for instance, our unit of length is the meter. It's not based on a single object, but is based on the length of the path traveled by light in this very tiny fraction of a second. So that is how length is defined. Time, similarly, is based on a certain number of periods of radiation emitted by the cesium atoms, and our basic unit of time is the second. Basic unit of mass is the kilogram. This was the last basic measure to finally be defined in terms of fundamental constant. There had been Legrand K in Paris for years. Just in the past few years, there's been a move afoot to change that, and as of May 20th, 2019, the kilogram is now measured in terms of the second and the meter by setting Planck's constant to be exactly this value. I like this because in most aspects of what I teach in this class haven't changed much since I learned physics decades ago. But here's a tiny change. There are small changes even at the most basic parts of physics. Okay, 2 other basic quantities is electric potential, the volt, and volume. Our basic unit of volume is a liter. So going back again, length, time, mass are measured in terms of meters, second, kilograms. Electric potential and volume are volts and liters. Another basic that we need for this class is our standard SI prefixes. Many are familiar, I would think. A centimeter is 1/100th of a meter. A millimeter is 1,000th of a meter. A kilogram is 1,000 grams, and so on. But sometimes some less familiar prefixes show up within this class. I've listed a few here that are rarely used. We do use nano a fair amount. That's 10 to the minus 9, or a billionth. So a nanometer is a billionth of a meter. Sometimes we will have giga, we'll have gigavolts, that is a billion volts, or mega, which is a million. So it's useful to have these metric prefixes handy as we move along. All right, so we will be working in this class primarily in the SI system, where the basic units, again, are kilograms, meters, and seconds. These are the standard units. There are other systems. CGS units are centimeters, grams, and seconds. And British engineering uses force instead of mass as one of its basic quantities, and also feet, pounds, and seconds. So for this class, we will focus on the SI system, or Système International. It's French for international system. And here are our basic units. I'm already mentioned some of these: length, time, mass. We also have our electric current is an amp, temperature is Kelvin, amount of a substance is a mole, and luminous intensity is a candela. All right, one last topic in this area is the difference between accuracy and precision. I think it's always good to have this in mind if you're doing any sort of experiment. So precision has to do with the repeatability of the measurement. So let's say I'm going to make a model analogy that might be helpful. Let's say you were trying to weigh something and you put something on the scale and you always got about the same amount. So now this is like a target practice, but you might think that getting to the center point would be getting the measure exactly right. So you put your item on the scale again and again, and you get a value that is a bit off, but is consistently off. This is a highly precise measurement, or fairly high precise. There's a little bit of scatter, but it's fairly precise, but the accuracy is off. So that can happen in experiments where you get nice repeatable results, but your scale wasn't calibrated correctly, so your accuracy is off. You can also have low precision where the values are scattered and you're also not hitting the bullseye. That would be low precision and low accuracy. Here we're getting to higher accuracy. We're zooming in on the bullseye, but relatively low precision, a fair amount of scatter. But if you average those values, we'd get a nice value that was right on target. And then finally, what we hope for when we're doing experiments is to have both high precision and high accuracy. The way to address accuracy errors is to have some sort of standard that you run through your experiment periodically to test to make sure that your values are accurate. So you'd have a little, say, kilogram weight in your lab that you could put on your scale to make sure that when you weigh it, it comes out as 1 kilogram. And if it doesn't, you adjust your scale a bit, and hopefully then you'll get closer to this result. Dealing with low precision often means buying more expensive equipment. That can be harder to fix. Okay. So what I want to talk about is conversions. So we will often be converting in this class usually between different metric units for, say, kilograms to grams. And that's relatively easy because all it involves is powers of 10. Sometimes we'll need to convert from British units, say from feet to meters or something. So for instance, if we're told that there's a conversion factor where 1 meter is 3.28084 feet, then we can convert and figure out that if we were told that a mountain is, say, 28,251 feet high, we could convert that to our SI units of meters and figure out that that corresponds to 8,611 meters. So how do we do that? So to convert, we use a conversion factor. You may have done lots of conversion factors. You may think you are the ace of conversion factors, but I just want you to think a little bit about why conversion factors work. And so if you recall that anything multiplied by 1 doesn't change its value. So 12 times 1 is equal to 12. So now think about a conversion factor. Let's say you have 1 inch equals 2.54 centimeters. That's your conversion factor. If these values are equal, then if you divide one by the other, then that equals 1. It's more obvious when the units are the same. 12 inches divided by 12 inches is going to equal 1 inch. 12 divided by 12 is obviously 1. But in this case, we have different units, but if they're equal, dividing one by the other is still equal to 1. So if we divide, say, 2.54 centimeters by 1 inch, that equals 1. Now if we multiply this term by, say, 12 inches, we're just multiplying 12 inches by 1. We're not changing the value, but we may be changing the unit. So let's do an example. If we wanted to convert 12 inches to centimeters, there's our 12 inches. Here's our conversion factor. This is just like multiplying by 1 because these two values are equal, and we put 1 over the other. So like 12 divided by 12 would be 1. 2.54 centimeters divided by 1 inch. We're just multiplying by the equivalent of 1. But in this case, we're doing a conversion factor. So you may wonder, do I put centimeters in the numerator on top or inches in the numerator? And if you just follow this through, the way this is set up, our inches will cancel and we'll be left with centimeters. And that's what we were trying to convert to, was centimeters. So this would be the right way to set it up. If we had inverted this, we'd get some crazy units of inches squared divided by centimeter, and that's not that's not a useful answer. So set it up so that the units you need to have cancel. So inches in the numerator, inches in the denominator. We've gotten rid of inches. We're just left with centimeters. And then you do the math. 12 times 2.54 is 30.48. And we're still in the first chapter, so we're going to watch our significant figures. There were we're given here. We assume generally with conversion factors that they have infinite numbers of significant figures, but we were told that we're converting 12 inches. So that was 3 significant figures. We want our answer with 3 significant figures, so we convert 30.48 to 30.5 in units or centimeters, and we're done. All right, if we have quantities with different units, we have to convert to the same unit before doing the math. So for instance, if we're asked to add 1 centimeter to 1 meter, we first need to convert so that both of the values are either in centimeters or meters. You can convert this 1 meter to 100 centimeters and have 100 centimeters plus 1 centimeter would be 101 centimeters, but our SI unit for distance is meters, so I'm going to convert the centimeters to meters. So there's my 1 centimeter, and I'm going to convert that to meters. There are 100 centimeters in a meter. I set it up so the centimeters cancel. I'm left with meters, so that's 0.0100 meters. I'm not too worried about significant figures now. I'm in the middle of the exercise, but I did keep it to, there were 3 here, I have 3 here, so good. And now I can do the addition. So our 1 centimeter plus 1 meter we can now write as, instead of 1 centimeter, 0.0100 meters plus 1 meter equals, and remember when we add, we pay attention to accuracy, not numbers of significant figures. So our least accurate number controls the accuracy of the solution. So this is accurate to the hundredths place. This was accurate to the 10,000ths. So accurate to the hundredths place should be our solution. That was our least accurate value. So our answer becomes 1.01 meters. All right, one other example, and that is to ask how many centimeters cubed are there in 1 meter cubed. So these problems where we have 1 unit raised to a power, you have to think this through a little bit more. We have to convert each of these centimeters to meters. So it might be helpful to think of a meter cubed is a meter times a meter times a meter. It's a volume. It's a volume that has 1 meter length on each side. And I need to convert all 3 of these meters to centimeters. So I can set that up there, my 3 meters. And here are conversion factors for each one. And all my meters cancel. I'm left with centimeters cubed, and I do the math. 100 times 100 times 100 gives me 10 to the 6, or a million. So the solution here is 1 times 10 to the 6 meter cubed. A few other tools that can be helpful. I always recommend actively engaging with the physics as you're problem solving. It's often helpful to just do some order of magnitude calculations. So for instance, if you were here trying to estimate, say, the height of a building and you had this set up, you could certainly tell that this building, if this was drawn to scale, is going to be greater than 3 meters, certainly, if you had but less than 300 meters. So if you worked out a problem and your solution ended up being 300 meters, you'd know that you had a mistake and you should go back and recheck. And I would also say that drawing a diagram is very helpful in making these sorts of estimations and just making sure that you're on the right track. So order of magnitude estimations can be very helpful in this class for picking up errors. And one other thing that's very helpful is dimensional analysis. And that sounds very dry, but it is so helpful. So for instance, if you're trying to, say, for the examples we did before when we were adding up distances, if you ended up with a solution that was, instead of meters, was meters per second, you should have a red flag right there that there's something wrong. You have the wrong dimensions for your solution. So dimensions of a quantity are the base units that make it up. And I try to be fairly consistent to use square brackets when I'm talking about dimensions. So for instance, if you have to calculate something speed is distance divided by time. That's going to be a length divided by a time. So our dimensions of speed should be a length divided by time. Or if we're in SI units, it should be meters divided by seconds. And I would note that quantities that are being added or subtracted must have the same dimensions. So if you are adding distances, not only do you want to have the same units, but you have to have the same dimensions. We can't add meters and liters. That doesn't make sense. We can't add a distance and a volume to each other. It doesn't make logical sense. But you can add liters to liters and get a larger volume, or meters to meters and get a larger distance. If you are multiplying or dividing, then you can have different units. So for instance, if you divide distance by time, you'll get speed, meters per second. Now, distance in meters, time in seconds. All right, and once again, look at your answer. When you calculate a solution, check your dimensions and make sure that they are correct. So if you're asked to calculate a speed, and instead of meters per second, you have just meters, there's a mistake somewhere. So that's a really quick way to pick up an error. All right, so if you're given a word problem to find a distance and to devise an equation that looked like this, 1 centimeter plus 1 second, you'd know this doesn't make sense. You cannot add things with different dimensions. So go back, re-examine your problem till you have a meaningful equation. And I would note that dimensional analysis obviously can tell you if your relationship is wrong, this would be wrong, but not if it is completely correct. You could write something down that would be correct dimensional analysis and still have an issue. All right, and when you're working through the math, write down the units and keep track of them. When you add distance, any units, 2 units of the same units, when you can only add the same units, then you end up with something in the same dimension. So 1 centimeter plus 1 centimeter is going to be 2 centimeters. When you multiply, the units are also multiplied. So 1 centimeter times 1 centimeter is going to be 1 centimeter squared. We'll go from 2 length measures to an area. If you divide a distance by a time, say 10 meters divided by 1 second, we'll get 10 meters per second, which gives us a speed, or if we know direction, a velocity. And if you divided that velocity by time again, we'd get meters per second divided by second is meters per second squared. That gives us an acceleration. So don't just do the math of, say, 10 divided by 1 gives you 10. Also do the math on the units. Meters per second divided by seconds gives us meters per second squared. All right, that finishes up our first topic area. We've talked a bit about theories, observations, predictions, and models and laws. We've talked about dimensional analysis and how it's useful for checking calculations. We've talked about how measurements are never exact. There's always some uncertainty, and it's important to write the uncertainty as well as the other quantities with the correct number of significant figures. We've talked about significant figures. We've talked about the most common system of units in the world is the SI system, and that the basic units for the SI system is kilogram meter second. And that reminds me, I should have really stressed that the SI system unit for mass is not grams, it's kilograms. So if you have to write something in base units for mass, it's not grams, it's kilograms. For all other SI units, it's the base unit without a metric prefix. So our SI system for distance is meters, not kilometers, it's meters. And our SI system for time is seconds, not picoseconds or kiloseconds or something like that. But for mass, it is kilograms. Okay. When converting units, check dimensions, see the conversion's been done properly, and finally, order of magnitude estimates can be helpful. Okay, that finishes up our first topic. From here, we'll be moving on to the kinematics of motion in 1 dimension. So I look forward to seeing you then.